All right, this question reads, a guitar string vibrates to create a sound. The speed of the wave in the guitar string is always 440 meters per second. The vibrating string creates a sound wave that moves in the air with a speed of 330 meters per second. Which graph shows the variation of frequency f with the wavelength lambda for the waves in the string and in the air? So the frequency and the wavelength, like as we get bigger wavelengths, do we get bigger frequencies? Or is it as we get bigger wavelengths, we get lower frequencies? So the first sort of clue might be just sort of thinking about the relationship between wavelength and frequency that we've kind of explored previously. We used light sort of as an example. We said, okay, there's a learning objective about stating the principal wavelengths of the EM spectrum. So electromagnetic radiation is also called light, and it travels at one constant speed c, 299,792,458 meters per second. But we said that's close enough to 300 million. We'll just call it 300 million. So because that's constant, if you have really long wavelength light, like radio waves, it's very low frequency, right? To keep that constant, like a high frequency is a low wavelength and a long wavelength is a low frequency, right? They're inversely proportional. So that's one thing to keep in mind. We should expect a plot like C or D, right? Like as the wavelength is longer, the frequency should be less. And so it's a negative correlation, right? So one of these graphs is correct. And now it looks like this one falls like this one falls like that, or does the air sort of fall not as sharply as the string? So we need to kind of think through which of these. So I'm pretty sure, and I'm not even 100% confident about this, maybe there's something like we're missing here, but I don't see how these could be true. Higher frequency, longer wavelength, like that. Even though this isn't light, like it still is traveling at a fixed velocity, right? 400 is like slower than this by a lot, but still a fixed velocity. So like always at that speed, right? The guitar string is going at always a faster velocity, but it still is the product of wavelength and frequency. So if we think about what we've got plotted here, let's rewrite this. So it's like y equals, okay, then we divide each side by this. So if I want to make this like my x, that's like y equals one over lambda times v. That's the same thing as that, right? But now I've got it kind of like y equals mx. So if I plot, but I didn't plot 1 over lambda, I plotted lambda. So hold on a second. Maybe we were too quick to dismiss these. You'll get a constant velocity if you plot 1 over lambda, right? Because it's like v over that, y equals mx. So at a higher, wait a minute, now I'm confused. The wavelengths of the waves in the string. So if the wavelengths are long, okay, we got a long wavelength, that's the wavelength in the string, then the frequency should be low, yeah. And then the slope, okay, 1 over, so that maybe explains the curve, right? Like a 1 over a rational function, like 1 over r, 1 over lambda. I'm leaning towards C because the speed in the air is slower. Right? The speed in the air is slower, 330. So you're always going to get that speed. So let's say we got velocity equals wavelength times frequency. And if we consider the air, which moves at a velocity of 330 meters per second, let's say that this wavelength here is 1 meter. Okay. So if the wavelength is 1 meter, then the frequency is 330 hertz to give us 330 meters per second. So if the wavelength is 1, then this would be like 330. If the wavelength is a half, okay, so if we plugged in, a half, we have to keep this as 330, then what's the frequency going to be for that? So 330 divided by a half is 660. So that, if we go sort of halfway here, we sort of doubled, sort of that. But it's a curvilinear relationship, no matter how you sort of slice it. What is the slope of this going to be? The rise over the run. What is frequency divided by wavelength? If velocity is wavelength times frequency, then frequency divided by wavelength frequency is velocity over wavelength. Yeah, this is a nice little stumper, huh? And paper 1 is kind of famous for questions like this, where it's kind of unfamiliar, right? You kind of have to think your way through it, and you wouldn't want to rack your brain over it as long as we are now. You kind of just maybe, like you said, well, I think I can eliminate A and B, and I think like they would just go down by the same amount. And, oh, and look, the string here is higher than the air. Here, the air is higher than the string, but there's also like a bigger gap between them. So if we could sort of deduce, well, which one would be sort of higher up? So how do we relate the velocity to sort of what we're given here? It's the product of these two things. And so it's like this wavelength times this frequency is giving us the constant. This wavelength times this frequency. This wavelength times this frequency. So as the frequencies get higher, that gets lower, but it always gives us sort of a constant value. But that value compared to the string can be lower. Is it because the steepness of this doesn't go as sharply? I'm not really too sure about this one, you guys. I need to kind of take a minute. I really like to take my time and kind of wrap my brain around it and really prove to myself sort of all the physics, what's going on here. So if we get another one that's like this, it's kind of like, oh, I've already spent a good, fair amount of time thinking through all of this. And that's how we build deep understanding, is to really just sort of not be quick to sort of give up on something, but to just kind of keep puzzling through it. And it's okay to be confused by information, because that's the emotion associated with deep learning. So I kind of look forward to it. You get to a question like this, and you're like, oh, okay, yeah, this is a little bit of a puzzler here. But it's a bit uncomfortable to be like, oh no, it's just confusing. I don't want to be confused. I want to make sense of it, right? So that's like you can see the light at the end of the tunnel. You should look forward to the learning that's about to occur when you sort of get to a nice, tough question like this. And maybe it's not so tough, just sort of overthinking it. If you took velocity equal to wavelength times frequency, and you divided everything by velocity, you have 1 equals this over that. Frequency inversely related to the wavelength. So it is not the slope of this that's giving the velocity, but they're plotting the wavelength this way. That's what's confusing me, is that the equation for velocity, and there's no way around it. Frequency, the rise over the run, like we're rising this way and we're running in wavelength. It's not equal to the velocity, because we would have to have plot 1 over that for that to be true. So the fact that we're plotting this, kind of like, that's what's confusing me. I need to sort of get a more clear example about what's going on with that. Not really sure about how to manipulate this to sort of relate it to the velocity, because obviously the other clue is that these velocities, right, are 440 and 330. So if the speed of the guitar string is always 440, and this one is always 330, how can we relate this curve to the velocity? If MS, so how do we sort of manipulate that? I multiplied both sides by 1 over this, and I'd have frequency over lambda equals velocity times 1 over lambda squared, right? So rise over run, y equals the slope is equal to the velocity divided by the wavelength squared, right? Frequency over wavelength. So if you follow that, okay, it's like starting with this equation, and I'm trying to look at like y and x, okay? So in other words, they plotted frequency against wavelength. So this is an equation that's going to be helpful to giving us the sort of constant values of velocity. So we're trying to sort of connect some ideas here. And one thought is to sort of, well, let's make it look like rise over run. Okay, so F over lambda. Well, in order to do that, it's like F and lambda are on the same time, right? Like they're inversely proportional. Their product gives the constant velocity. So it's like this times this gives a constant, this times this gives a constant, this times this. But I don't know which of these curves is correct. So there's maybe like something else, some other clue that we kind of need. Does anybody have any ideas on this out there that's got some keen insight into it? Feel free to always interject or unmute your mic and say, what about this? You know, again, it's better to sort of find it, you know, a good physics study buddy that you can really, you know, talk your way through these questions and ask them what kind of sense they're making of it. And, you know, that's a good way to sort of learn here. So what I did here was I took this and I rewrote it so that F is on one side all by itself. And so that means I have to divide each side by lambda. So I had F equals V over lambda. And then I kind of want this lambda over here with this F. And so if I multiply both sides by 1 over lambda, remember, you're allowed to sort of do lots of stuff in algebra as long as you do it to both sides. And so if I multiply this side by 1 over lambda, it achieves my goal of getting that term, right? F over lambda. But then I got to say, well, I got to keep equations equal and just do anything I want to because it looks good for this problem. What is the F over lambda equal to according to the physics? It's equal to V over the wavelength squared. So because the slope of these lines, like the slope of, you know, this, and it's changing, right? Like here, there's a slope, here, there's a slope, there's a shallower slope. These curves are changing. The rise over run, okay, is equal to the constant velocity divided by the wavelength squared. Okay, so it's like the slope of this right here is equal to the constant. Let's say for the air, it's 330, but then I'm dividing it by this big number squared, which means I'm dividing by a longer wavelength squared, which means it's going to make it much, much lower. And so that sort of explains maybe the curve this way. If you had, now the string has a 330 meters per second. The speed of the wave in the string, no, is 440. The sound wave that moves through the air is 330. So the air is slower than the string. So this is a higher wavelength and a higher frequency. And so that's going to give us a faster speed. Maybe that's all we needed at that point, was just to say, look, the string speed is faster than the air speed. And so look, at a higher wavelength and a higher frequency, wait a minute, both are higher. So we take this number and multiply it by this number and get 330, and take the same number and multiply it by a lower frequency. So if we choose a given value for lambda and we say, okay, let's consider this one. Here's a certain wavelength, and when I multiply this wavelength by a higher frequency, I get the speed of air, the speed of the wave through the air, 330, right? So it's like frequency times wavelength gives this. If I took the same wavelength, so that value is the same, but I multiply by a lower frequency, could I get a faster speed, 440? There's no way, right? Like we can disprove this. We say that's impossible. That doesn't agree with this information. Now, I'm not 100% about this, obviously. And I still haven't really thought my way entirely through this, but I feel like we're on the verge of a breakthrough where it's like, okay, that tells us how the shape of this curve is going, right? How the slope is changing according to the square of the wavelength. So it's like, as we make the wavelength bigger, we're dividing into the constant velocity a number that's getting bigger sort of as the square, right? So like as we're climbing up this way, then the slope is going to get flatter and flatter because we're dividing by sort of that bigger number squared to sort of equal our slope. So that's why it kind of flattens out at the end. This one just looks like it starts sharp and this one just kind of flattens out more quickly. Well, why would it do that? And why could air be up here? But if we said for a given wavelength multiplied by a frequency, we get a value for the string, which is always 440 meters per second, right? So it's like this value, whatever it is, times this value is 440. Let's say it's 440 meters times 1 reciprocal second, right? The units of this would be reciprocal seconds. Well, if we take the same wavelength, 440 meters times less frequency, right, then we're going to get a slower speed. And that's true for air, it's 330. So I really feel like we spent only, you know, an hour and 40 minutes discussing this. Hopefully that's correct. Oh boy. Question 21. I'm going for C. And I won't resign my position as a physics instructor if I'm wrong. I'll just silently cry back here for a little bit. All right, let's go see 21. Hey, 21 is C. So feel a little bit better, but it took a long time. It took a long time to get to that. And I think, again, when you're using the questions as a problem study, it's okay. Take all your time in the world. Try to explore the physics, make better sense of it, okay? It's helpful to sort of do those manipulations and think about, well, what are we sort of plotting here? How can I explain this sort of a shape? I think we pretty well did it. We kind of explained why it would go like this, why the string would be higher than the air. So, you know, not only do we know sort of the correct answer is C from reviewing the mark scheme, but we kind of know why it's the correct answer. We can disprove all the other ones. There'd be no reason why air would be higher than string, and really no reason why its curve would sort of flatten out more than this one. So, all right, only took an hour, but we got there. That was a wave question, huh?